Hi, this is Hassan Kurani. In this video we are going to learn the properties of scalar product and the sign of scalar product in a plane of two vectors in a plane. Previously, as you saw, we studied the definition of scalar product of two vectors. Let's start with the properties. First property says that, as you see, we have u dot v, it is the same as v dot u. So we are allowed to switch vectors if we have dot here. This switching is called commutative property. Well, as you see, it's similar to multiplication, ordinary multiplication of real numbers. If we have a number a multiplied by b, it's the same as b times a. Similarly, in vectors and dot between them. U dot v, the proof of this property comes from this detail. U dot v, as definition says, magnitude of u times magnitude of v times cosine alpha. And similarly, v dot u equals magnitude of v times magnitude of u times cosine alpha. And if you notice that the right sides of these two equations are the same, so u dot v and v dot u are equal. In fact, let's see the second property, which is u dot into v plus w equals u dot v plus u dot w. This, as you see, reminds us by expanding numbers, but here we are dealing with vectors and we have dot, so we put dot between them. We don't put multiplication, ordinary multiplication of numbers, since it has another meaning with vectors. So we are distributing, as you see, its name is distributive property. We are distributing the dot over the addition, and we can also use this property for subtraction. If we have minus, so u dot v, it will be u dot v minus w, it will be u dot v minus u dot w. Okay, the third property says that m u dot nv, where m and n are two real numbers, as you see. If we have m u dot nv, it is equal to m times n. First we multiply the numbers and we keep the vectors in a parenthesis to make scalar product for them after we multiply m by n. As a result, we get mn into u dot v. Let me remind you that u dot v is a scalar valued, means it is a real number, and also mn is a real number. Okay, don't miss these three properties, which are very useful in our exercises. Consequences of these properties are called remarkable scalar product, which are the first one, u plus v squared, which is equal to u squared plus 2u dot v plus v squared. As you see, this reminds us by what in real numbers? This reminds us by a plus b squared, which is the remarkable identity. And similarly, we can use it in vectors, but instead of multiplication of 2ab, here we are multiply vector with another vector using the scalar product operation. Okay, the second property says that u minus v squared equal u squared minus 2u dot v plus v squared. As you see, it's very easy. And u plus v dot u minus v, it is equal u squared to u squared minus v squared. These are properties. You can use them directly in our exercises, and no need to go deeply in the proof of these consequences. Let's see an example. First one, we are given, as you see, vector u for 3 and another vector v in vector form minus 1i plus 2j in an orthonormal system Oij. We are asked to calculate 2u dot minus 3v and u minus v squared, each one alone. Try to I advise you to pause this video and try yourself to calculate this scalar product. Then check your answers with us. Solution: clear that v minus 1, 2, these are the coordinates of v. From this form we can deduce them. So 2u dot minus 3v will be, as we said before, we multiply first the numbers, 2 multiplied by minus 3, and u, which is minus 6, then u dot v, where u and v are of known coordinates. As you see, we are dealing with coordinates of vectors, so it's good to use the analytic definition of scalar product, which is x prime plus y prime. So we have x, we have y, we have x prime, y prime, directly x by x prime, which is minus 4 plus 6. At the end we got minus 4 plus 6, which is 2, multiplied by minus 6, which is minus 12. Okay, clear? The second term, second part of our question is u minus v squared. As you see, this is a remarkable scalar product. It will be u squared minus 2u dot v plus v squared. Now, let me remind you by what is meant by u squared and v squared. If we have a vector u 4, 3, u squared is in fact u dot u. This is a particular case we learned before. This is the form u squared is magnitude of u squared in fact, and this is equal to x squared plus y squared without this square root symbol, since we have square here. So directly, when you have a vector square of a vector, directly it will be equal to magnitude of u squared, and if you have the coordinates of this vector, you can say that it's equal to x squared plus y squared, as here. And we perform these calculations, minus 2. Now u dot v, in fact we can take it from the previous part we did before. U dot v is x prime plus y prime, which is minus 4 plus 6, which is 2. So just plug in 2 here to get minus 2 into 2 plus. Now v squared, again, this is x squared plus y squared, or x prime squared plus y prime squared, which is minus 1 squared plus 2 squared. At the end, after you make these simple calculation, you'll get your result 26. Okay, now we are going to learn a very important concept or idea about scalar product, which is the sign of scalar product. As we said before, that the scalar product is a real number. We didn't say that it's a positive. It is possible to have negative scalar product. In fact, if we have two vectors u and v in a plane and alpha is their geometric angle, we have, from the geometric definition, u dot v equal to magnitude of u multiplied by the magnitude of v multiplied by what? Cosine alpha. Now, think about the sign of u dot v. This expression reveals that these are positive. Why? Since they are length. Magnitude is a length of a vector, so the length, as you know, are always positive. So the sign of u dot v depends on the sign of cosine alpha. As you know, cosine of any angle is bounded between -1 and 1. We saw this on a trigonometric circle. So the sign of u dot v, as I have said, doesn't depend on these, since they are always positive, so it depends on just cosine alpha as mentioned here. Now, before we see the three cases, we are going to see this activity that show us all what we are going to say in the cases below. Well, as you see, we have two vectors u and v, and we have translated them at the same origin a, and we have a geometric angle between them. As we move one of them or rotate one of them, we can see that the angle, the geometric angle over here, changes. Now, I want you to notice the sign of u dot v if I change the angle, if we change the geometric angle by moving or translating v. Now, as you see, the angle is 0 since they have the same sense, and the scalar product is positive. Now, I'm changing the angle, I'm increasing the angle. As it is less than, as you see, till now it will be positive. Downward also positive. So as you see, the angle here is acute, 41. Above it is also acute, and in this case the scalar product becomes negative. Also in this case, as you see, the angle is obtuse and the scalar product is negative. In a particular case here, as you see, the geometric angle between them is 90, as we said before, and we said that these two vectors are orthogonal, then the dot product is 0. So as a conclusion, as well as the angle between two vectors is acute, less than 90, here less than 90, also here less than 90, the scalar product is positive, and when the geometric angle becomes greater than 90, the scalar product will be what? Will be negative, as you see. That's it. So we have three cases: case where we have acute angle, right angle, and obtuse angle. Okay, let's go back to see these three cases. The first case, if alpha is acute, means alpha greater than or equal 0 less than pi over 2, which is equivalent to pi over 2 radian, which is equivalent to 90 degrees. Then, as you know, cosine alpha is positive, and u dot v will be also positive. The second case, if alpha is obtuse, if alpha is greater than pi over 2, which is 90, less than or equal pi, between 90 and 180, the cosine of alpha will be negative, and so u dot v will be what? Negative. If alpha in the third case is pi over 2 radians, it means if alpha is 90, then cosine alpha equals 0, and in this case u dot v will be what? 0. Well, this is for today. This is our homework, page 180, exercise 18, 19, 20. Thank you for watching. See you in the next video, and goodbye.